We fine-tuned an embedding model that was 80% better at product similarity use cases than standard pre-trained models for large retail marketplaces. And we are not talking about small improvements here. We went from 0.52 to 0.9 after fine-tuning in terms of performance. And in this video, I'll show you exactly how we did it, from preparing the training data, manipulating the data set, to fine-tuning the model, benchmarking the performance, and everything in between. Whether you're just dealing with messy product classification, inventory migration, or just want to understand the process of fine-tuning embedding models in production for industry-specific use cases, perhaps in retail, we'll just go through this. And there is not a lot of documentation available out there, let alone videos, on how fine-tuning embedding models specifically works. And this is a guide that we wished we had when we got started. So we just want to go over that. So let's get started. I'm Rohan from Ionio. We help retail companies with AI. Over the last 4 years, we have worked with 35 plus companies, built dozens and dozens of SaaS and AI projects. And if you need help with AI in your company, drop me a message. Our aim with the fine-tuning was to optimize the model for 3 critical use cases. One was product similarity matching, to identify similar products so that we can deduplicate the marketplace. Second was taxonomy standardization, to fix inconsistencies in product categorization during inventory migration. So that sounds like a bunch of words, but if you're a retail company, you know exactly what that means. And inventory migration optimization, to simplify the process of transitioning of products across platforms. So you're going from Amazon to Flipkart to Etsy, something like that. And if you have a very large inventory, how would you go about doing that? So here's the core problem. E-com marketplaces have their own rules for categorizing products. So for instance, one platform might list a product as wireless earbuds, while another platform calls the same product Bluetooth headphones, even though they refer to the same exact product type. These differing taxonomies create conflicts during inventory migration for retailers. And the result is inconsistent product classification across platforms. And this makes it difficult to group similar products together, which just makes cataloging the inventory a lot more complicated. So this also eventually leads to poor search results. You have to manually fix these taxonomies. And this, of course, requires humans to do it. So it's very expensive to do. And then inventory migration, as I said, always becomes complex. And you might wonder, aren't there already existing solutions which take care of taxonomy migration and product similarity? Well, there are, but most of these existing systems which have been out of research, but most of these systems which are actually deployed and systems which are not in research, they are still largely depending on keyword-based models or rigid rules to grasp the nuances of product data. For example, because they're depending on just keywords, they can't recognize that biotic shampoo and volumizing conditioner belong to the same category, that is hair care. Worse, they might pair dark chocolate and chocolate-based body lotion into the same category just because they have the word chocolate in the description. And product categorization is sometimes done manually, and that also becomes complex because of this. So to solve for this specifically, we fine-tuned embedding models. And these models capture the semantic similarity, not just the keyword-based lexicographic similarity, but also the semantic similarity. So when we talk about wireless earbuds and Bluetooth earphones, the model understands that they are similar to each other. We are not talking about product categorization here. Even in similarity, the model understands that these two products are similar to each other than being completely different. Fundamentally, we are using embedding models instead of using keyword-based techniques to find similar products. And at this stage, you would probably wonder, why are we trying to fine-tune an embedding model instead of just using a pre-trained embedding model from OpenAI? Why are we trying to do that? So pre-trained embedding models, they are excellent at general purpose semantic understanding, but they fall short when you try to give them very specific challenges in industries like retail, medical, pharmaceuticals, or even chemicals. And this happens because the general purpose pre-trained embedding models don't really understand the nuances of product similarities. To them, coconut hair oil and intense hair repair shampoo, they are still very similar to each other. So when we fine-tune these models, we are essentially able to make them more nuanced and expand the differences between different categories internally. At a high level, you can see exactly this in the example below. You can see how in the base pre-trained model, we have the 2 products very similar, very close to each other. But then on the fine-tuned model, they're significantly away from each other, and thus representing a higher level of resolution on product similarity. And in this video, we'll go over the high-level steps that we follow to fine-tune the model. The final result, we analyzed our fine-tuned model on a retail data set stretching over 11 product categories and 90 subcategories in each of them. And these categories span over multiple products, everything from beauty goods, hygiene goods to kitchen essentials. And you can see the results on your screen of our own fine-tuned model. Let's finally get started. And if you're looking for a more detailed breakdown of the entire process, we have already written a very, very detailed blog about this on our site. When fine-tuning an embedding model, the underlying data set plays a very crucial role in teaching the model the nuances of the specific use case. In our case, we fine-tuned the model on Big Basket's complete product list, which is a Kaggle dataset. We utilized sentence transformers to fine-tune our embedding model. Now, the original dataset had over 27,000 rows representing individual products with attributes like name, category, description, and so on. But this wasn't really sufficient just to train the embedding model. The reason for this is the dataset lacked essential pair-wise context, so embedding models can't learn from isolated data points. It looks for relationships and for dependencies between the different items to understand the pattern. And without this pattern, the model would not really learn how one product compares with another. And this would lead to misclassifications. So, for example, the model will struggle to understand if hair care products are related to shampoo or shampoo is not related to a chocolate bar. And number two, we created mismatched combinations. We pair products from different categories which were dissimilar to each other to just teach the model what dissimilarities looked like. And then by using these techniques, we expanded the dataset from mere 27,000 rows to over 218,000 rows of data, ensuring that there was a balanced representation of matched pairs and of mismatched pairs. After that, we needed to fix the specific format of the dataset. Sentence transformers require the model to have a pairwise combination of products so that the model can learn about the similarities and the dissimilarities. So this requires the dataset to be in a specific pair class and pair score or triplet format. And specifically, we decided to go with the pair score format, which consists of two product descriptions and a similarity score between them. So for this, the original dataset had to be transformed into product pairs, some matched pairs and some mismatched pairs. And additionally, we also needed to add similarity scores to these pairs to really guide the model through the fine-tuning stages. After step 1, we had about 130,000 rows of data of matched pairs. And after step 2, we had the remaining 82,000 rows of data. After that, we just started the fine-tuning process and we monitored the training with weights and biases. So we tracked metrics like loss, learning rate, and other relevant information during training. And you can see examples of this on your screen. And yeah, we just trained the model. And so here are the final results. The base model with the Pearson score of 0.52 really struggles to align the predictions with human annotated score. On the other hand, the fine-tuned model with the Pearson score of 0.99 demonstrates remarkable ability to really align with the ground truth for product similarity. The Spearman score of 0.46 of the base model indicates difficulty in ranking the pairs consistently with human intuition. And for the fine-tuned model, the Spearman score of 0.7 shows that the fine-tuned models rank sentence pairs more effectively. So yeah, there you have it. This is how we fine-tuned embedding models. All of the code for the training, for fine-tuning, and the models itself is on Hugging Face. You can find that somewhere. And yeah, that's pretty much it. The concepts that we have used here would translate even if you are trying to fine-tune a model to get better responses on the RAG. So if you're trying to build something which would automatically match products in search queries through a RAG, through a chatbot, using our fine-tuned embeddings for retail would work significantly better than just using OpenAI's embeddings for RAG. So this is where it is really helpful. And even for recommendations, you would actually be able to use the embedding model to create smarter recommendations which are more relevant to users. And finally, if you want to build product categorization use cases, which we will not discuss in this blog, if you want to build that, building those would also be a lot more possible by using concepts from fine-tuning. So yeah, that's pretty much it.